Oh my gosh. For it. A whole thing devoted to the rainbow sponge.
This one!
Arts and Crafts Department sent
I don't like this one.
Now, rainbow sponge, this is so dense. 3 sizes because I can't stand just one size. Another thing that I want to talk about is the hygiene of the sponge. I squeezed and squeezed and squeezed and squeezed. No flab on this arm for my cleaning. Flab on this arm. Now, if you do get it on your hands, gloves are incredible. I have a pure glove.
Jesus Christ!
Absolutely pure. Oops, a virgin edge. Oh my gosh. I'm sorry. Oh, I want you to look at that.
I just want to be this happy someday.
Wiggle. Oh my gosh. Wiggle.
That's literally
Oh my
me.
gosh.
I just want to be this
I
happy.
love to wiggle the whole thing.
Possums.
Any
Possums are
surfaces
ants.
that you can sponge on. I'm sure you would. Of course you can go straight.
Rainbow flash.
What? Okay, calm down, D. And it's done. Yes. Do you see that?
Because it's funny.
I just want to be this happy.
Sorry.
Is this fun? What? Look at that. On a card. Really heavy. Yes. Yes.
That's me on every occasion.
Oh my gosh. Now, things
my
go
God.
this way, and now we see. Oh my gosh. Oh my gosh. And then.
It sounds like you're having a really fun time.
It is so hard to stop.
Sounds like my parents' bedroom.
Oh, God. Justice.
Why are you guys trying?
So you're saying that your parents say that virgin corner, that virgin edge.
All right. I just want to be that happy someday. The reason I think of this is because when we're talking about triangle similarity, we're talking about triangle squiggle, all the squiggle theorems, right? And that's what I think of when I think squiggle. I think the squiggle's fun. All right.
Can we please have the thank you?
Here we go. When we left off yesterday, I believe we left off at the end of number 3. Did we prove number 3?
What is this?
Don't look at that. Look at the thing we did yesterday. That's an extension on the
Oh, we
worksheet.
didn't finish it. That's
We did not finish 3, right?
No, we marked it up.
Okay, here we go. So you should have had, at the end of yesterday, this one marked up. Angle C and angle DEA are the same measure, and they're 90. So this is what this means. This is what you should have had. And that's all they gave us. We want to prove that AD, this segment's length, times BC, this segment's length, don't worry about that, is going to equal
That's a bad.
AB
My charger console too.
times DE.
I took it.
Yeah.
I gave it back to him.
But honestly,
And you're not giving it back. What happened to one?
did little baby Jesus.
All right, so, Alicia, you might have half of that from yesterday.
Oh, I guess we did write it down.
All right, so we're going to prove that AD times BC is the same thing as AB times DE, and that's just kind of weird, right? What does that even mean? What we really want to do is we want to prove that this big triangle and this triangle are similar, and then we're going to compare their parts, because that's what's going on, okay? So, recall that in order to prove things similar, we have angle-angle squiggle, right? Angle-angle similarity. We have side-angle-side similarity, and side-side-side similarity. Remember, triangles are similar if their sides all relate by the same amount. Right? So these two triangles would be similar because they relate by 2, right? Doubling. Yes.
They share and
Yes, I'm not ready for that yet. So,
Yeah.
for some of you are gone, I need to catch them up with what we did yesterday. I'm sorry.
Explain the calendar.
So if we have 2 angles congruent, that's going to be enough to prove that they're similar. Same thing with 2 sides and an angle. Now notice, when I talk about sides, I'm not talking about congruent. Similar triangles have congruent angles. That's true. The angles will match up. But similar triangles will not necessarily have congruent sides, right? They have proportional sides. And proportional sides looks like something like this. Like that. BF and DF, their relationship is proportional to AF and FE's relationship, right? That's the idea. So when we talk about S for sides over here, we are talking about proportional sides, okay? When we talk about A, we're talking about congruent angles. Cool? Are we going to be okay?
Yes.
All right, because this is going to kick your butt today. The first two aren't, but the third one will. All right, so here we go. Laney's right. Haley is right. This angle is shared with both triangles. So by shared angle, angle A is congruent to angle A. So both the big triangle and the small triangle share that angle. Now we've got two congruent angles for both triangles, right? Two here and two there. This is on the small, this is on the big. Are you with me? Okay, so now we can say those two triangles are similar by angle-angle similarity.
Hand sanitizer.
She's already used it 5 times.
Interrupt next.
Left again.
By angle-angle similarity,
Use either.
these two triangles are similar. So triangle ADE is the small triangle. When we write that it's similar to the other triangle, we want to make sure we match up the stuff, just like when we do CCP, right? So angle A is going to go with angle A on the big triangle too. D is this unknown angle on the small triangle, so it's going to go with the unknown angle on the big triangle, B. And then E is the right angle, it's going to go with C. Cool?
I have a question.
What?
The purple, I know it was gone. Are you streaming this?
Yep, so this
Okay, never
angle
mind.
is shared with the small triangle and the big triangle. Both
Oh,
triangles
okay,
use it.
thank you.
Okay? Yeah. So we have angle-angle and angle-angle, so we're allowed to say by angle-angle similarity, the triangles are similar. Are you with me? All right, so now that the triangles are similar, we know that they should have matching angles. So for instance, both are going to use A, because A and A line up, right? B and D are going to be the same angle. And E and C are going to be the same angle. You with me on that? Right, because they're corresponding, right, in the same relative position. Now, I don't care about talking about the angles anymore. I want to talk about the sides. Similar triangles have congruent angles. We've already talked about that. D and B would be the same, A and A would be the same, C and E would be the same. But their sides won't be the same. They'll be proportional. Meaning that they'll relate. So if you look up here, these two triangles are similar, right? Their sides relate. How do they relate? Well, 3 relates to 6 the same way 4 relates to 8, the same way 5 relates to 10. Namely, a half, right? So what we're saying here is now that we have these letters all lined up, we can say by corresponding similar parts, right? Not congruent, but similar, because we're talking about similar triangles. We know that AD in the first and second position here will have a relationship with AB the same way that DE relates to BC, because DE is in second and third spot, BC is in second and third spot, right? The same way AE, first and third, relates to AC, first and third. Again, I did the small triangle first, so I had all the small parts on top and the big parts on the bottom. Now, unlike these numbers up here, which all relate by a half, right? I don't know how these relate. I just know they do. Does that make sense? Are they double? Are they triple? Are they half? I have no idea. But whatever it is, it's the same for all of them. Are you smelling what we're stepping in so far? Yes, Kozovic? Tan? Okay. So I've got this. So now I wanted an equation relating the sides, right? And I have an equation relating the sides. What sides do I care about? Well, I care about AD and BC. That's here and here, right? And I also care about AB and DE. So I don't really care about this guy over here. So I'm just going to focus on that, okay? So I'm going to rewrite that. These are related by division. I want to get multiplication in here. Notice that AD and BC are on the same side. Are AD and BC currently on the same side? No. So we need to change that, right? So, quick break. This is a related problem. How do you solve the problem like Maria? I want to get x on its own. What do? Multiply by 2, right? X divided by 2. That's all fractions are. It's division, right? So I have x divided by 2 over here, right? I just made up this problem, okay? I would multiply by 2, because when I multiply by 2, what I get is 2 times x, which is 2x, right? And then 2x divided by 2, that's 1x. So you see how those basically cancel? right? When you times something by 2 and divide by 2, it becomes 1, right? And 1 times x is just x. But I have to do it to both sides. And when I do that, here's how this works. Yeah, you can draw a line here and put a 1 underneath it. That's fine. You don't have to. Here's how you should think about it. Multiplication is done on the top. Division is done on the bottom.
Bless you.
So multiplication is done on the top,
Oh, go home.
right? So I'm going to have 9 times 2 on top and division on the bottom. Divides by 5. Do you see how I got from here to here? Yes.
Why can't you cross multiply?
You can, but it only works when you have two fractions equaling each other. So you could 5x and 18 and then divide by 5 to get the same thing. However, the amount of time you're going to see two fractions equaling each other other than in here, very rare. Because what will happen is we'll have people get this, and they'll be like, oh, cross multiply. Nope, you just do across. Do you see the danger there?
Yeah.
And this is what you're going to do 90% of the time. So I don't like teaching the thing, the only thing you're going to remember, for some reason your dumb little brains only remember cross multiplication, it's so much fun, right? But we do it like barely ever. And then you screw this up, which we do all the time. So I just don't teach it. How would I solve this? Well, I just multiply across. How would I solve this? Get rid of the division, right? I don't know. Why make it complicated? All right, so I multiply by 2 to this side, which cancels. 2 divided by 2 is 1. 1 times x is x, right? That's why I did it. Times by 2 over here, multiplication happens on top. Division happens on the bottom. That's all it is. 9 divided by 5 times 2. That's 9 times 2 divided by 5. Doesn't matter what order you do it in. And then we would know that 9 times 2 is 18. And we have 5 on the bottom, right? That's the answer. Over here. Same concept, but with big letters, okay? I want to get BC over to AD. Right now I'm dividing by BC. So how am I going to move that over? I'm going to multiply by BC, right? And I do it to both sides. When I do it here, well, the reason I did it so it would go away, right? Move over here. So it better go away. And that makes sense, right? BC divided by BC is 1, right? Anything divided by itself is 1. And then I times it by DE. DE is just DE. So I get DE on its own. Over here, I'm going to get BC times AD in the top. Remember, multiplication happens in the top. Division happens in the bottom. That's it. That's all it is. Okay. Now I've got BC and AD together. That's great. But I want DE and AB to be together. So what am I going to do to move the AB over? Multiply, right? Same dumb crap I just did. That makes sense. No tricks. It's just straight up, how do I get rid of the division? I multiply, right? This is nothing new. Again, these canceled and these canceled. And by canceled, I don't mean it became 0, because obviously timesing by 0 would be bad. It'd make everything go away. What I mean is BC divided by BC, right? Multiplication on top, division on the bottom, becomes 1. So it goes away, right? 1 times anything is just itself. Over here, we have AB divided by AB now. That becomes 1. 1 times this stuff is just that stuff. That's why it goes away and cancels, okay? It becomes 1, and 1 times anything is just itself. So now we're here. We wanted AD and BC on the same side. Got it. AD and DE on the same side. Got it. Now, their order, they had AD first and AB first. We haven't flipped. Is it true to say that 2 times 3 is the same thing as 3 times 2? So I'm allowed to flip these. That's the commutative property. Do I need you to write it? Oh, no. Now we're done. So it turns out, even though we don't know what the sides of these triangles are, if we knew it, we could do this to figure out stuff. So this is kind of useful, right? I know that AD times BC will always give me the same thing as AB times DE. So for instance, I'm adding on to this problem. We are done with this proof. But pretend that I said that this was 6 and this was 5. I know it doesn't look like it, but just go with it, okay? And that I knew DE was, I don't know, how about 3? And I wanted to know how long this is. Well, I've proven that AD times BC will be the same thing as AB times DE. So we know AD is 6 in this case, BC is 5, and AB we don't know, right? And DE we said was 3. Now I don't have to make that an x, I can just leave it as AB, value of AB, right? That's 30, and this is 3 times AB. How do I get AB on its own?
Division.
Divide by 3, right? It's times 3, so I divide by 3. Turns out AB is 10. So eventually we're going to get to a spot where I give you a bunch of stuff and I'm going to ask you for values for other things. And you'll be like, look, I got all that, that's great, but how do I figure this out? I have no freaking clue, right? That's one way to do it. Prove the parts similar, and then you know they're related somehow. Find out how they're related, right? And then plug in your numbers. So that's not what we're doing right now. I just want to show you why we're learning this, right? We can get some interesting properties. These sides relate to these sides, turns out, in a very special way. How do you feel about the proof part? Do you feel good up to here? Triangles are similar by AA.
Yeah.
CSP gets us this. We can rewrite that to get this. Feeling okay with that concept? All right, rad. Let's go on to number 4. Actually, not number 4. Let's skip. We're going to go to the last one, number 6. I threw first hour in the deep end too quickly. That did not end well. So we're going to go 6. I added on some extra ones to the packet. That's what I just pointed out. So page 5, number 6.
6.
All right. Page 5, number 6. We're going to ease our way into this, okay? This one's not too bad. The one after this is going to be awful, though. So you need to really understand this stuff so you know what's going on. Okay? We'll take a break after, not this one, but the one after this, okay? AC and BC are congruent, so I know that this is the same as that. And as soon as I do that, if alarm bells aren't going off in your head, you did not pay attention last week. Or maybe you were absent because you had the flu. Right?
The angles.
Something, something. We have an isosceles triangle, right? Hold your horses, I'm not done yet. ED and AC, they're perpendicular. So ED hits AC at a 90 degree, right? So that gets us 2 90 degree angles. And we know that these are perpendicular as well. That's from the given, okay? We need to prove AD over BF equals A, it's garbage, okay? Let's talk about what it means. AD, this segment right here, must relate to BF. And the way it relates to it will be the same way that AE relates to BE. Does that make sense? These two sides are related and these two sides are related. So we're going to prove these two triangles similar. And then we're going to use CSP to prove their parts are proportional, right? Yeah.
Well, if we have the isosceles part, that means we have the angles, right? Which
Exactly.
means we have AA.
Yep. So check it out. We have isosceles triangle theorem, and that gets us this angle and this angle. So by isosceles triangle theorem, angle A is congruent to angle B, because that's the only angle A and angle B in the diagram. I don't have to use the 3-letter full name. Cool? Yeah. You wanna? Here. I got plenty of pens up here, I think. All right. So now that we've got that, Katie's right. We're going to say by AA, these two are going to be similar, right? So by angle-angle similarity, again, don't forget the similarity thing. Don't forget the squiggles thing, sponges, right? We know that this triangle on the left is similar to this triangle on the right. So I'm going to write triangle ADE on the left is similar. Do not write congruent. They are not necessarily. I'm yawning in math class. ADE. Match it up. A is going to go with B, right? D is the 90 degrees, so it's going to go with F. And E is the unknown angle. So it's going to go with the other unknown angle. Now, yeah, you could say by CSP now, I know that E is the same as E, D is the same as F, A, right? All the angles are going to match up, right? But I'm not interested in that. I'm interested in the sides. Similar triangles have congruent angles. So yeah, angles are going to match up, right? But they have proportional sides. So we're never going to say the sides are congruent, right? We're going to say something like this. Does that make sense? Okay.
How do you know that those are 90 degrees?
That was given to us because it's perpendicular. This hits at this. That's what that symbol means. So now we're going to say the triangles are similar. Now that they're similar, we're going to use CSP. So by corresponding similar parts, what sides do I know go with what? Well, AD, because it's in first and second position, is going to relate to BF. In the same way that DE, what's DE going to go with on the other triangle?
FE.
Yeah, don't look on the triangle, just look here. FE, right? Second and third. In the same way that AE, first and third, don't forget about that one. I think everybody forgets first and third, the split, right? AE goes with what? BE, right? That's the beauty of CSV. You can just look at the letters. Yeah.
So why do we have to do A and an E? Or
So I'm writing down all of it because I want you to get in the habit of that, because depending on the proof, you might need different stuff, right? I know we only need 2, right? But I wrote all of it, just so you know that all of that is true, okay? Sometimes we'll need all of it. So I want AD and BF to be equal to AE and BE. Well, if this equals that, and that equals this, by transitive property, right? Remember that? I'm touching the table, the table's touching the pen, therefore I'm touching the pen, right? We can write like this by transitive property. I'm not going to make you write that, but you can just write this and cut to the chase, cut out the middleman, and we're done. Now, how do they relate? I don't know. Are they double? Are they triple? It looks like they're pretty close, actually, right? I don't know how they relate, but I know that they relate the same way. So if this was 2 and that was 4, then I know that if this was 3, that'd be 6, right? Some relationship. Is it double? Is it half? Is it quadruple? I have no idea. How do you feel about 6? Okay. We're going to try 5 now. Oh my goodness.
So tough. It's the same thing with the other triangle added.
All right. Don't worry about what we're trying to prove yet. Let's just talk about the given. Are you ready? Here we go. It says D is the midpoint of AC. That means this, right?
No.
Yeah.
Midpoint means cuts it in half.
Yes.
Yeah. Is that how you label it?
Yep.
Really?
E is the midpoint of AB. Here's AB. Here's E. It cuts that into 2 equal pieces. I don't know that AC and AB are the same, so I can't say that the halves are the same, right?
Oh.
F is the midpoint of BC. So it cuts it into 2 halves, right? Now, do we have an isosceles triangle? No. It's a scalene. Could it be isosceles? Could we find out that red's the same as green someday? Sure, right? But what we're showing here is that for any triangle, doesn't matter if it's isosceles, equilateral, or scalene, all different, right? This will be true. What will be true? Look at the given, or the what we're trying to prove. AB relates to DF. Check this out. AB is the bottom here, right? It's going to relate to DF. And not just relate, but we know how it's going to relate. It's going to be double. AB is going to be double DF. So whatever this is, you double that and you get this. This is true for any triangle. Not only that, but AB will be parallel to DF, right? So they'll be parallel. That's a lot of good information. Remember, parallel gets us angles, right? And then being double is going to get us sides, right? If these are halves, right, that's going to be a blue as well. And this is true for any triangle. Now, I can just draw 3 random segments in a triangle and that'll be true? No. It's when those 3 segments are connecting in the midpoints. So if I draw a random triangle, any random triangle, and I find its midpoints, and I connect them, those segments are called mid-segments because they're connecting the midpoints, right? I will know that this will be half of this side. Does that make sense? I will also know that that's parallel to this, which means these angles will be the same, and these angles will be the same. That's a theorem, mid-segment theorem.
So
It'll be true, and it'll be true for all the others as well, right? This will relate to this the same way this guy will relate to that. In the same way this guy will relate to this. So these will be parallel, these will be parallel, and these will be parallel. And all of these will be half of their opposite sides. That's a lot of information. Now, it's going to take a little bit of a proof to get there, but it's a theorem, which means eventually someday we'll be able to say, by mid-segment theorem, I know this is the same as that, that's the same as that, that's the same as that, and those are all parallel, right? For free. It's like vertical angles, boom, they're there. I don't have to say why, just by vertical, it's done, right? By mid-segment, this and this means that's a 1. This and this means that's a 3. This and this means that's a 2. And they're parallel.
so you can write that.
It's a very powerful theorem. We're not going to use it yet in proofs, right? We're going to prove the theorem, right? Because all theorems are provable, postulates we accept with faith, right? So here we go. There's a lot of true information here. Remember the other day when I gave you a bunch of triangles, I said, tell me something true about them that I don't want to hear, right? And then Schlaffer said the thing I wanted to hear and we ended the game, right? But there's a lot of information you can get here. First of all, those 3 angles all add up to 180, right? Very true. Is it going to be helpful? No. What I want to do is I want to streamline this process and focus you in the bare minimum, because if we start writing stuff everywhere, it's going to make our diagram messy. when you do this for the quiz, don't be afraid to write stuff. Here, I'm looking for specific things. What you're probably going to tell me is true, but it's not what I'm looking for, and that's okay. So here's the first thing I'm going to point out. This angle is shared by the top triangle and the whole triangle, right?
Yeah.
I think everybody's used to seeing that now. So by shared angle, angle C is the same for both triangles. Again, when I'm talking about the triangles, I'm talking about this one and this one. Now, why did I choose to talk about the top triangle and the whole triangle? Here's why. I want to prove that AB, the bottom of the big triangle, is similar to the bottom of the small triangle. So I want to talk about the small triangle at the top and the big triangle. Does that make sense? Those are the two triangles I want to talk about. Notice they both share that angle, okay? Now check it out. To prove similarity, we know that we have angle, angle, squiggle, right? We also have side, 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 squiggle. And we have side, angle, side, squiggle. Let's talk about what these means, okay? AA means that we have two angles that are the same for both, right? Cool. Side, side, side means I have three proportional sides. Three sides that do this on each triangle, okay? It's not that they're congruent, it's that they're proportional. So check it out. I also have another one where two proportional sides and a congruent angle. That's what I have here. So I'm not saying that this side is the same as this side. I'm saying they're proportional, right? This is half of this. Do you agree?
Yep.
Isn't this also half of that? Right?
Yeah.
So the way that CD relates to AC is the same way that FC relates to BC. They're both half, right? So I have a proportional side and a proportional side and an angle in the middle that's congruent. By side, angle, side, squiggle, I can prove those two triangles, this one here and the big one, similar. So before I can say anything about the sides, I have nothing about sides down here, right? I need to write something. So what I'm going to do is I'm going to say that CD relates to AC, the whole thing, right? And it relates the same way that CF relates to BC. Are you smelling what I'm stepping in? They are related. They're not congruent, right? Because that guy's smaller than this guy, right? But they are related. That's half of this, right? And not only that, but this is also half of that. So they're both going to be a half, right? How do they relate? They relate by half. I actually know that they do, right? This is half of that. Now, here's the problem, right? This means that this guy's 1 and that guy's 2, right? But I don't know that. Couldn't it be 3 and 6 as well? How do I know that I can write 1 over 2? Well, if it was 3 and 6 and 4 and 8, don't they all reduce to a half? So no matter what they are, at the end of the day, when you simplify, right, it's all going to reduce to a half. Right? It could be 8 and 16, it could be 10 and 20, it could be 5 and 10, right? But at the end of the day, it's all going to be half, right? Because that's half of this, guaranteed. Right? See how that's 1 red and that's 2 reds? So that's half. Are you with me there? They're not congruent, they're similar, and how are they similar? They're each half. I started going from small to big, so I got a half, right? The small part is half the big part. If I flipped those and I did big to small, I would have said the big part is double the small part, and I would have gotten 2 over 1. Is that cool? Maybe about 50. Okay, red. So now I've shown that I have sides that are proportional, right? And I've shown that I have an angle in between them. So now I can use sides, angle, side similarity. But you have to have this first before you can do it, right? Gotta have the sides, gotta have the angle. So here we go. By side, angle, side similarity, I know that two triangles are similar. The top triangle, which is triangle CDF, and the big triangle, which is triangle, now we got to match them up. Well, C is going to go with C, because they share that angle, right? D is made up of the red side and the unknown side, right? So if I go down here, here's red side, right? Proportional red side, and then the unknown, right? Not the green one, right? So it's going to go with A. D goes with A. So already see that? Red and unknown, red and then unknown, because we don't have any blue here, right? F, it's made up of green and unknown, so proportional green side is this, right? Unknown side is this, so that's B. Do you see how I got those letters? And in what order? This angle D is made up of red and unknown. And this angle down here for the big triangle is made up of the proportional red and the unknown. We have to call it unknown because we don't have any blue up here, right? Does that make sense? So red and blue makes this angle. Red and soon to be proven blue is this angle, right? Green and soon to be proven blue. Green and blue. Those are going to go together. C goes with C for the big triangle and the small triangle. Better? Okay. So now we know the top triangle and the whole thing are similar. I want to talk about their parts, namely their sides, right? So by CSP, the parts should relate somehow, right? So let's write that. Now that I've proven them similar by corresponding similar parts, I know their parts relate. So here we go. This is where we play the letters game, right? What parts are going to relate? Well, CD, that segment, what's it going to relate to in the other triangle? CA, CD and CA. Yep. You with me? You with me? All right. In the same, oh, that's cool. In the same way that DF will relate to what?
AB.
AB. Second and third, second and third. In the same way, this is the one everybody forgets.
CF.
CF, right? First and third. The outers, right?
CB.
And not only do I know they relate, but I know how they relate. Right? If CD and CA and CF and BC are a half, and they equal DF over AB, they all equal a half. So what does this mean? Well, it means that CD is going to relate to CA, the whole thing, by a half, right? DF is going to relate to AB by a half. So check it out. If AB is double blue, how big is DF going to be?
Triple blue. Half a blue.
If that's double,
Yeah.
that's half, right?
Yeah.
DF is half of AB. Okay. So that's a single blue. CF, CB are going to relate, CF and CB, right? The whole thing. Right? We knew that before. This is the new information we got, that DF and AB are related.
You don't know.
Double the half. Okay.
That is correct.
Now this has them relating to equal to.
Oh.
I got a half. Why? Go.
Because this is not the little triangle.
I went small to big and got a half, right? The small part is half the big part.
So you're big.
If we flip them, right, we'll go from big to small. The big part is double the small part. So what I'm going to do is I'm going to say, therefore, CA over CD, see how I flipped it? AB over DF,
Yeah.
flip that one. CB over CF, I'm going from big to small. Big is 2, small is 1, right? It's double the small. And 2 over 1 just equals 2. So I got that part of the proof done. Swag.
Will there be a problem like that on track?
Oh, yes.
Multiple?
Yes.
Uh-oh.
All right, here we go. I'm going to back up and go over it again, and then we're going to get the last part. Okay, the last part's super fast. I just want to make sure you got this, okay? So check it out. I said by shared angle, C is shared by the top triangle and the big triangle. Yeah? With me?
Yep.
Then I know that this part is half this part, and that's half this. So they relate the same way. They relate by half. Cool? So then I said, well, I've got proportional sides here, proportional sides there, and an angle in between. So I can say Sas Similarity. So the triangles must be similar. So this triangle and the whole thing must be similar. You with me? If they're similar, then I can say by CSP, their sides should be proportional, right? Which sides go together? Well, CD and CA go together, right? CF and CB go together. And it looks like DF and AB go together, right? Based on the letters, DF and AB. Before I said they were equal to half, so DF and AB must be half as well. So that tells me that if this is 2 blues, that's 1 blue. I flipped them all to show that it's double, right? Depends on which way you look at it. Am I going from small to big? Small is half the big, or am I going from big to small? Big is double 2, right? The small. Do I have you so far? Okay, let's get the last bit. Parallel. What? How are we going to do that? We've never had to prove parallel before. Here's the deal. Remember a time when we had cap, And everything was so hard. You're like, oh my God, corresponding angles. How am I going to find? Right? And now it's like, oh my God, who cares? Right? This is so easy. CAP, corresponding angles postulate, says that if two lines are parallel, then the angles correspondingly will be congruent, right? So if I have something like this, and I say they're parallel, they have to be parallel. And I have a line cutting it. Remember that? Then the corresponding angles will be congruent. See how they're both top right corner of the intersection? Here's an intersection, top right corner, intersection, top right corner. If they're parallel, those two angles will be congruent, right? That's CAP, corresponding angles postulate. Converse means reverse, right? So before we said if the lines are parallel, then the angles are congruent, right? Now we're going to say if the angles are congruent, then the lines must be parallel. So we're using corresponding angles postulate, CAP, but the converse, right? So here's what I'm going to do. By CSP, because I've already proven those two triangles similar, right? I know which angles go together. C and C goes together. We already knew that from earlier, right? The purple angle, right? D and A are going to go together. So D in the small triangle, that's this angle right here, will be the same as A in the big triangle. It's this angle right here. So those go together. So I'm going to say angle D. Now I can't call it angle D when I write it because there's lots of angle Ds, right? So I need to write angle CDF congruent to angle CAB. And if you look, CDF, first, second, third, CAB, first, second, third, right? They're in the same order, so I can write them congruent. Is that cool?
That's
Right?
cool.
So now that I know those two angles are congruent, CAP converse, right? Do you see it now?
Mr. Krabs.
We have two parallel lines cut by a transversal. Now normally we'd have to say they're parallel to get the angles, but we already know the angles. So we can do the converse and say, because those angles are congruent, those must be parallel lines. So we're going to say by CAP converse, DF, ooh, let's write it the way they had it. AB is parallel to DF. Are you with me on that idea? Let me zoom out. If the two angles are congruent, then by CAP converse, those must be parallel lines. Does that make sense? Now, what about all this other stuff?
Irrelevant.
Here's what I'm going to say. If those are parallel, because of those two angles, what if I rotate the diagram? Wouldn't it be true to say
Zoom.
that we have two parallel lines here because these angles will be the same? What am I doing here? I want not that. I want these two will be parallel. There we go. Do you see it? I've got corresponding angles here and here, right? How do I know they're congruent? Because that triangle is going to be similar to this triangle. I can prove that. I can go through the whole thing. This triangle here, similar to the whole triangle, right? So those angles match up. And then I can say, oh, by CAP converse, these must be parallel, right? And I can keep doing that as I rotate the diagram. Or I could just say, by similar logic, if AB is parallel to DF, like I previously said, then BC will be parallel to DE, and AC will be parallel to EF. Okay. Write that out, and then let's talk about what that means.
You zoom.
All right. It's the same thing that they have at the top. So offers the proof thing. That's all you write. Okay? So here's my logic. You agree with me that those two are parallel, right? We proved that? That these two are parallel? Yeah? Well, I can turn the diagram and do the same dumb crap and then prove that those two are parallel. You with me? I can turn the diagram again and prove that these two are parallel, right? But instead of having to do that and replace CDF and CAB with the other angles, right? I just said, look, do the same dumb thing I did before, but with all the other sides. That's by same dumb logic, okay? How do you feel about that last part?
What?
By CSP, those two angles are the same, because if you look back up here, CDF and CAB go together, right? In fact, I wrote it so they're perfectly in the right order. That's awesome, right? And so I can say that these two angles are the same. And if those two angles are the same, by cap converse, those are parallel.
Cap converse says that if they correspond, then it must be parallel.
If the corresponding angles are congruent, then the lines must be parallel. Regular cap says if the lines are parallel, the corresponding angles are congruent. Yep. All right, so check it out. What does this mean? Again, it means any triangle you draw, no matter how weird, if you connect its midpoints to form mid-segments, that segment there will be parallel to this side. And not only that, but it will be half that side. A lot of good information there. Same thing for all the other segments. If this is this, then we get that, and it's parallel. A lot of information from one theorem, okay? And that's the proof behind it. All we were given is the mid-segments, right? That they're midpoints. And from that, we got everything else. Congruent triangles are cool, right? Two triangles the same, great, interesting, awesome, fantastic. Similar triangles can tell you a whole lot more. Congruent triangles, it's like, man, they look the same. I bet they are. Oh, I proved it. Great. Why did I have to do that? Similar triangles are like, I would have had no idea that was true for all triangles, like that guy, right? But we can show that to be true. We can find all kinds of interesting relationships with different parts of the triangle. I'm going to show you in the next 2 weeks how circles and triangles are related. And it's all based on similar triangles. It's going to blow your freaking mind. Okay? So we got to learn this stuff so we can learn these proofs and know how these theorems work. Tomorrow, we will tackle this beast, number 4. Where is it? This one right here. I tried it the first hour today. It was an experience.
Was it a disaster?
No, it wasn't a disaster. There's just an overview.
That was half. That's half.
Half?
Okay.
What?
I need you to have your A game tomorrow.
You just said half.
It's half.
Dude, I quit.
You're going to be okay.
Are you sure about that?
I feel like when we did this one, the first bit up to here, you guys were like, oh, that makes sense. I'm good with it. It's just like we did in the last 2 problems, right?
Yeah.
Get the triangle similar by getting their parts similar. Boom. CSP were good. And then what was weird was using that at the bottom, right?
Yes.
A lot of them are similar. When we did congruent triangles, what we did was not follow 5 steps and good, you did the proof, right? This is an algebra. This is PEMDAS. What we did was we did get all the information you can, find which triangles you want to be congruent, prove that they are, and then use CCP to prove the parts are, right? And that's how we finish it. For CSP, for similar triangles, the same dumb crap, get as much information as you can to prove the triangle's similar. And then use CSP to get their parts, right? It's the same idea. How we go about it's going to be different for every problem, but the premise is the same. Find things that match, angles that match, right? 2 angles gets it done. Find 2 sides and an angle in between. That gets it done. Or in the rare case, find all 3 sides, right? And say that they're proportional. That's pretty rare. You're going to be okay. You guys can do this. Nice job today, guys.
Oh, we just
Matt, can I pass the homework?
Yep.